Hello, everyone. Today, I'm going to talk about NeoBFT, accelerating Byzantine fault tolerance using authenticated in-network ordering. This work is finished with Mingliang Jiang, Xinzhe Kui, Yunfan Li, and Jialin Li from National University of Singapore. Permission blockchain has gained popularity to be used to keep consensus among participants without mutual trust. The use case including trading, online payment, and supply chain management. These use cases demand both high throughput and low latency, which causes the permission blockchains thoroughly deploy in data centers for low and predictable network latency. The requirement of permission blockchains are challenging. They must tolerate adversarial participants, keep strong consistency, scale to large deployment, will maintain high performance. These requirements lead to the use of Byzantine fault tolerance replication or BFT protocols, which can tolerate arbitrary faulty behavior and keep consistency. Although BFT protocols can fulfill safety requirements, the existing BFT protocols cannot offer desired performance by blockchain applications, which is high throughput and low latency. The most well-known BFT protocol, PBFT, involves 2 rounds of all-to-all communication per request, which result in low throughput. Although the throughput can be improved by batching, the latency will also go higher, which makes us not get close to our target. Hotstep has been optimized by maximum throughput and still cannot provide desired low latency. And the other BFT protocol, Ziziba, performs well, but only without any faulty behavior, which is usually not a valid assumption in blockchain systems. MinBFT tries to simplify the protocol and reduce overhead by leveraging trusted component, and it suffers from the huge latency penalty of the hardware limitation of trusted component. In conclusion, the prior solutions only considered protocol optimizations and trusted components on unhost, and we have other design dimensions to explore. In-network ordering has been developed in data center networks in recent years. It introduces a stronger network model that provides ordered multicast by leveraging network programmability. It incurs near zero cost, and we can co-design distributed protocols with performance benefit. It has been applied to a wide range of distributed systems, including NoPaxos, Aries, and Hera. With in-network ordering, when clients sending messages, they first arrive the sequencer, and the sequencer assigns each message with a sequence number based on their arriving order. Then the sequencer broadcasts client messages to replicas. When replicas receive the messages, they deliver the messages to application in the order of messages sequence numbers. Thus, the messages are always received in the same order on every replica. Leveraging property of in-network ordering, we can simplify protocol design and get significant performance improvement. Take distributed transactions as an example. As shown in message diagram, the complicated two-phase commit protocol can be replaced by a simple single-round protocol, significantly reduce latency and the number of messages, in turn increase the throughput. So can we apply in-network ordering to accelerate BFT protocols? In this work, we propose a new approach to improving BFT performance in data centers by offloading ordering guarantee to the network. We design a new network primitive called Authenticated Order Multicast, or AOM, which can provide in-network ordering to BFT protocols. We co-design a coordination-free BFT protocol called NeoBFT, and finally get BFT with both high throughput and low latency. Next, let's talk about AOM design and implementation. Blindly applying in-network ordering into Byzantine fault model will not work because adversaries can generate conflicting message order. When sequencer multicasts the messages, let's say some of the ordered messages are lost due to network partitioning. In such case, if there's any faulty replica who relabel the received messages with different sequence numbers and broadcast the messages may be received by the replicas who did not hear from the sequencer. Then the replicas cannot reach consensus on the message ordering and fail to maintain consistency. To solve this problem, we need to find a way to let replicas determine the correct message order, and the answer is authentication. Our solution is to let sequencer switch signs the messages, and replicas to independently verify message signatures and make sure messages are indeed generated by sequencer. We design a new network primitive called Authenticated Order Multicast, which augment prior order multicast primitives. It has similar property to the prior primitives, but for the first time, in-network ordering can provide authentication and transferable authentication properties. With authentication, receiver can verify the messages are correctly processed by AOM sequencer, and with transferable authentication, receivers can verify authenticity of messages forwarded by the other receivers. When clients send messages with AOM, besides assigning sequence numbers, sequencer also assigns each message with a signature, then multicast to the replicas. The replicas can verify the signatures, know that the messages are indeed from the sequencer, and accept the messages. If there's any faulty replica trying to publish its own ordering to the other replicas, the message will not be accepted because faulty replica cannot generate a correct signature for the message. The implementation of AOM requires in-network authentication, which is challenging. Crypto algorithm may contain complex computation, involves large prime numbers, and have unbounded loops and large vectors, all of which are difficult for programmable data plan due to hardware limitation. So to make cryptographic feasible on programmable switch, we choose to deploy a lightweight message authentication code, or MAC. The implementation uses two pipelines of a programmable switch. Pipeline 0 is for sequencing and multicast, and Pipeline 1 deploys 4 parallel MAC generation instances in 12 pipeline passes. When message arrives the switch, it enters from Pipeline 0 and gets sequenced. Then it is forwarded to Pipeline 1, recirculate back to ingress, then generate a vector of 4 MAC signatures. Then it is forwarded back to Pipeline 0 and get multicast. The problem with MAC vector is poor scalability because it requires 1 MAC per receiver. Public key cryptography instead offers infinite scalability, but it is too complex to implement directly in the switch data plane. So we propose a new switch architecture that integrates a cryptographic code processor, and we implement it with FPGA in our prototype. In our prototype, SCCP 256K1 signature generation is implemented on FPGA. When messages arrive switch, it first gets sequenced, then forwarded to FPGA. After generating signature, FPGA forwards the message back to the switch and multicast. Next, let's move on to the co-designed NeoBFT protocol. It needs 3 F+1 total replicas to tolerate F Byzantine fault replicas. It leverages guarantees of AOM to realize single RTT commit in normal operation. It also contains efficient protocols to handle network anomalies and will change protocol for leader and switch failover. In normal operation, clients send requests to replicas with AOM. Replica verify the AOM message, speculative execute a request and reply to the client. Client can confirm the execution is durable after receiving replies from 2 F+1 replicas and commit. As a result, client commit in 1 RTT, and there's no coordination among replicas. There's more detail in the paper that I have not talked about. Please check the paper if you are interested. And finally, the evaluation part. We performed a series of evaluations compare NeoBFT with 4 previous BFT protocols: PBFT, HotStuff, Zizaba, and MinBFT. In our evaluation shows NeoBFT has best performance and good scalability, and it is also resilient to network anomalies. The result of performance evaluation is shown in this throughput latency graph, and NeoBFT achieved desired high throughput and low latency. Comparing to other protocols, NeoBFT shows 1.8 times to 3.1 times throughput improvement, and 8.5 times to 42 times latency improvement. Furthermore, NeoBFT still has better performance when the network is adversarial. Please check more evaluation results in the paper. In summary, we propose a new approach to accelerating BFT protocols in data center by offloading BFT ordering guarantees into the network. We design and implement in-network authentication to tolerance adversarial behavior. And we also co-design new BFT replication protocol, which shows significant throughput and latency improvement over existing protocols. That's all from my presentation. Thanks for listening.